Okay, so welcome to the post-lunch session of today's conference. So the speaker, one and only, is Nilakash, and he's going to talk about prethermalization and black hole evaporation.
Okay. Thank you, Abhishek, and thank you to the organizers for inviting me, for giving me the opportunity to give this talk. Prethermalization is a phenomenon. Okay, if you can just Google it, you will find it. It's a thermalization with two time scales. First, there's a very short time scale thermalization, and then the system is sort of in a metized, not actually adiabatically, but it looks approximately thermal, and then it slowly goes to a real thermal, equilibrium state. Okay. It was first, the first paper that is well known is by these fellows, okay, in 2006, and it's on heavy ion collision in astro-cosmo context, and the title of their paper is only prethermalization, just one word. And in their context, what they find is that the pressure, temperature, etc., they satisfy the equation of state, okay, but the occupation number, okay, of the momentum modes, they don't look, they don't look like Fermi-Dirac or Bose-Einstein. Okay, it takes a long time to look like a Fermi-Dirac and or Bose-Einstein. So they call that phenomenon prethermalization, and condensed matter people, okay, follow up on this, okay, and they have basically beaten it to death, okay. But there are different contexts in which they call it prethermalization. Okay, one of the most well-known one, which starting from 2000, for the last 10-15 years, okay, is if you have a integrable system, it's a weakly chaotic system. So this is for a weakly chaotic system. So you have an integrable Hamiltonian, and you have a small eternal and small chaotic an integrable interaction. Okay, and probably many of you might have heard, okay, that integrable system actually under certain circumstances, okay, basically mostly coincides, okay. But under certain circumstances, okay, they thermalize to generalized Gibbs ensemble. Okay. Basically, you need a lot of fine tuning. Okay, but for now, let's just say that integral system can thermalize to generalized Gibbs ensemble. Okay. But because of this chaotic nature, and actually in this integral system, the thermalization to GG for local operator happens instantaneously. And if you have spatially separated points, okay, then thermalization happen, in some time scale given by depending on the length of the separation, okay. And if you put on a twist operator, then you get your, well-known Cardy-Calabrese or result like entropy grow linearly and then saturation. Okay. So, but for local operator, the thermalization happen instantaneously. Thermalization to GG for only this in the integral Hamiltonian. Okay. It basically means the initial state you have fine-tuned it. Okay. And actually for local Hamiltonian, in this review, okay, they have reviewed. Okay, actually it comes from some paper by Rigol and Zungu and others. Okay, that this thermalization, it actually happens because of central limit theorem plus the local nature of this Hamiltonian. Okay, and if you start from a short range interaction, okay, that there is no long range interaction. For example, if you have a free scalar field with a mass, and you are still in a ground state, so it's it's a short interaction because you have a effective mass. So mass leads to very exponential decay correlation in the ground state. And then you suddenly turn off the mass. Okay, let's say your mass is some parameter that you can tune. When you turn it off in the free scalar theory, the system looks like a generalized Gibbs ensemble. It's an ensemble with a lot of charges. Okay, just like your thermal ensemble. grand, canonical, or you choose, but with a lot of charges. Okay. And now coming to this prethermalization, when I turn on this extra term, what happens is ZZ actually is time dependent. Okay, and so it evolves for a long time until you reach a final true thermal state. Okay, and so this is what this goes by many names. Okay, that time dependent ZZE or prethermalization, weakly interacting chaotic, weakly interacting system, etc. Okay. Yes. Yeah. And on the other hand, thermalization in chaotic system, like the best is of course the SYK model, or let's say highly chaotic model, is very robust. Okay. Like SYK is very robust. Okay. Yeah, actually, let me just tell you, okay, just for 1 minute, the difference between one stark difference between thermalization of this integral system and the for a chaotic system like this. Okay, it is the best way to differentiate is you do a finite perturbation. Okay, if you do a finite perturbation in this integral system, it won't thermalize. Okay, but in a SYK system, okay, you're pumping in energy and it will thermalize again. So that's actually the easiest way of actually differentiating between these two cases. Okay. In case of SYK model, as we know, these are just randomly interacting fermions. Okay, so we check for thermalization by comparing it with Fermi drag statistics. Okay, the occupation numbers. And we have our paper also where we do disturbance of quantum coincidences or disturbance of SYK model, and we it thermalizes very robustly. Okay, you do anything, okay, you disturb it, it always comes to a thermal equilibrium. Okay. Now, so this has been this weekly in this setting. Prethermalization has been studied in many by many people, especially by condensed matter folks. Okay, how about prethermalization in chaotic systems? Okay, there is some sense where prethermalization can happen in a chaotic system. Okay, and well, the one that I I first saw is in this paper by Rigol and collaborator. Okay. So let me tell you in what context it happens. So they study a chaotic system which has a concept charge. Okay, and this system, it thermalizes with a time scale tau star. For SYK, tau star is of the order of the inverse temperature, and for interacting Fermi liquids, these are generally higher powers, so beta square, etc. Okay, so this is for SYK, and this is for Fermi liquids. Okay, I think this power might change. Okay, I don't know the details very well for these guys, okay, but for SYK, it's very well known that it's beta. Okay. Yes. This is the thermalization time scale. Okay, and what they do is to this Hamiltonian, let's call a new Hamiltonian, to this Hamiltonian, they perturb it with a operator which do not commute with this, either of this. So O doesn't commute with Q. Okay. These are operators. Okay, so let me not put hat, but they are not operators. Sorry, they are operators. Okay. Let's say you take a complex SYK, and Q can be your occupation number. Some conceptors. The Hamiltonian, yeah. And you take the case where, z tau, let's say, I have, scale it so that z is, z is, energy, length scale, z unit is energy. Then, for this case, okay, you consider this case, okay, that z is very small, basically. Okay. Then, what happens is that if you do, some perturbation, you prepare it in some state, okay, of this system or this system, and then you turn this on or do something, okay, you disturb the system starting from the equilibrium, okay, and you evolve it by this Hamiltonian, okay. Then what happens is that in time t, which are order of tau star, actually the system approximately thermalizes, and approximately thermalizes. Thermalize to rho, which looks like minus beta of the chaotic part only. Okay. Of course, there you will have charges. Okay. Yeah, usually people write it like this, right? You can have charges. Okay. But it's approximate. Okay. There's some time dependence. And for time, which are much larger than this, okay, which are times which are of the order of 1 by z, okay, the system slowly evolves to come to a real equilibrium. Okay. So in long time, okay, long time, you really go to this, let's call it total. You really go to this beta is total. Some beta, okay, this beta and this beta are different. Okay, let's call it beta prime. All right, okay. So, they have studied, okay, they study many quantity and so this, okay. Oh, and the best part is actually, since this is a small perturbation, okay, for me, the first order perturbation, okay, basically for me golden rule applies, okay. So the rate of thermalization, okay, or the rate of any change in the observable, okay, it is proportional to z square in this long time limit, okay, for t. T which is of the order of 1 by z. So let's look at this. If you think, what's happening in the Hilbert space. Okay. I like to look at this way because I want to give rise. I want to show the parallel with the black hole evaporation. Okay. So this chaotic Hamiltonian, it has this charge. So it will have charge sector. So it will have Hamiltonian H1, and then direct product with H2, and so on. Okay. And so on. Okay. When you introduce this, what's happening is that earlier these were all filled with 0. Okay. This was this giant full Hamiltonian. This earlier it was all 0, but because of this, it pick up non-zero. Okay. O something something. Okay. Why is this pick up? Why is this? All right. And so in time scale, which is of the order of this, what is happening is that the system is thermalizing inside here. Okay, there's this these states only talk to themselves. Okay, but at a longer time, they start talking with this other state. Okay, because these are all suppressed by small z. So now let's compare this to the case of a black hole evaporation when you couple it to a bath. Okay. In a black hole, here we have direct product of H1, H2, etc. But in here we will have the say black hole, and sorry, this was direct sum, and this will be direct product plus I cross H bar. And of course, you turn on your favorite interaction. Okay. V, which is some operator of black hole and some operator of the bath. All right. So as you can see, there is a parallel between this and this. When this coupling is very small, we expect that perturbation theory will work, and then this prethermalization phenomenon will work. So the black hole evaporation process is also a process is also a prethermalization phenomenon. Prethermalization phenomenon. Okay. Oh, so the black hole is a chaotic system. Okay, since the coupling is small, just like I was saying here, it will thermalize. Okay, if let's say you have a black hole, you couple it to a bath. Okay, if you throw in something to the black hole is very chaotic, so it will thermalize, and because of the weak coupling, it will weakly lose heat to the bath. Okay, if the bath is have very low temperature, the setup is very simple. Okay. Sorry, here what? Mm-hmm.
Is T star the time scale where it becomes rethermalized?
Yes, yeah. Yeah, as I was saying, T of this scale, okay, the system look like this, but it's a time dependent, small, it has some small time dependence which is dictated by this one, by Z square. Yes, you can.
So what about the black hole evaporated state such as prethermalization?
So the black hole will be a little different from thermal state, right? Just like here, it will be actually given by the deviation you can calculate it using perturbation theory. These are all perturbation theory.
I think basically, are you saying that the effects of that O bar,
Yeah.
ODH will not have set in? So the black hole will evaporate.
Yes. In the time scale, yeah.
That process is the prethermalization.
Yes.
And then after that, on some longer time scale.
Yeah. Huh?
How does G compare to the
Z, what was, it will be 1 by Z square or Z, yeah, if you integrate over it, okay, maybe it will be 1 by Z square or something. Yeah.
But I thought it's an independent time scale. It doesn't, so let's say I made a black hole of some entropy or mass, then that fixes the page time. But then I could turn on various couplings to the bar.
Yeah, I mean, if you have forget about black hole. If I have a hot system, if I have a cold system, okay, the rate that it lose energy, it will depend upon the coupling rate. It's just so. Let's say you have a black hole, you couple it to some scalar bar, a free bar, or something. It will depend upon the scale. Yeah. In real life, it will depend upon the coupling to the the U1 fields. What is the coupling? Yeah. The pace time.
That depends on the dimension.
Yeah, the pace time. Yeah, pace time. I don't know. Pace time usually is talked in terms of the mass, right? 1 by m cube or something. But it's never talked in terms of this coupling. What is this coupling? The coupling between the black hole and the bath. So yeah, I have to look that up. Yes. Yes. It's because the two length scale of this thermalization of this length, yeah, two length scale will mix up and then you won't see it.
Yeah, exactly. So I'm saying that there must be only some particular range of G where it is prethermalized.
Yeah, that's where I'm coming to. Yeah, that's where I'm coming to. So this is perturbation theory, and it should work as long as if you keep increasing G, it should work until you hit the critical point or the ground state shift. Okay. Yeah. So the only problem in this perturbation theory scenario, it could be if when you increase Z, if it gives rise to a quantum phase transition or a change in the ground state. Maybe the O dominates, something like that. So yeah, so the next thing I want to talk about the quantum phase transition. Okay. And yeah, actually, okay. So I'll, what I'm coming to is I want to give a criteria for a quantum phase transition. Okay. It's actually for the next 10-15 minutes I won't be talking about black hole, etc. Okay. I'll be just talking about some criteria of phase transition. Okay. Up till what point you can say that perturbation theory is reliable? It's a general thing, okay, for any arbitrary Hamiltonian, okay. So quantum phase transition. If you look up, for now the most the very well-known book by Sandip with this name, quantum phase transition, you'll say that if you have Hamiltonian H naught and you couple you have H1, then if you tune this, okay, what might happen is that let's say this is Z and this is, let's say, inner Z. The ground state might look like this and another state might look like this. Okay. And what we don't want is this to coincide. Okay. And usually many of the in the thermodynamic, many of the phase transition happen when this actually coincides. Okay. So that's a critical point. Okay. Or actually, in some cases, it could be they could cross. Okay. That's the usual level crossing. Okay. But please note that we are right now not interested in, let's say, we are dealing with, for example, SYK, where, the spectrum looks very dense, okay? As you know, this SYK spectrum, even the low-lying ones, they have e to the power and S naught, where S naught is of something 0.4, something related with Catalan number and all. So there are lots and lots of states here, okay? So I am not particularly interested in level crossing of nearby states here. Okay. Anyway, this number is very big, so there's level separation will be inverse of this. Okay. So they are very low lying. This low lying state crossing each other. I don't care much. Okay. In other words, these states are in some configuration space. Their configuration are more or less similar. Okay. So let's say what I'm saying is if I have a SYK Hamiltonian like this. Okay. Some 2 to the power n, 2 to the power n, so okay, Hilbert space, and I put in all the entries. Okay, if I change the one entry by, let's say, 0.01 or something, okay, 0.001, it might happen that actually this low-lying state might they might cross. Okay, so what I really don't want is actually some linear combination of all this, some very high temperature state, okay, crossing with this ground state. Okay. So let me tell you in terms of the the example, canonical example, which is given by in this book. The first one, which is the the well-known transverse Ising model. Okay. So, and actually it need not be a phase transition. Okay, it could be a level crossing. Okay, where the expansion about one ground state is not good, like tachyonic expansion or something like that. Okay.
What is the scale of this course? You're basically doing some course.
This, okay, yeah, I'll come to this. Okay, so this state, they are very close to each other. Okay, I really don't care whether, let's say, this state crosses with this state. Okay? I'm more careful about some state here coming down and crossing with this one. Okay, because these are very nearby state. Okay, if I change something, okay, in the experiment setup, because of some accident, some gamma ray falling, things might change. Okay, I don't care about this. So this state crossing, I don't care. But some state coming down and crossing, that's the problem. So transverse field Ising model. As you know, the Hamiltonian is simply given by this. Okay, minus z sigma z. Sorry, let me write it I plus 1. Sigma z, and then we have sigma x, sorry, ix. Okay, and the general argument is if z is 0, then all the spin want to be flipped in the z positive direction so that the Hamiltonian is minimized. Okay, so it will be so the ground state for this one will be up pole. But if z tends to infinity, the ground state will be this, you know, and that x, you know, x is positive, right? So this is, from this, it goes to this, okay? Now, if you independently think of this two state, actually, this state, okay, is the infinite temperature state of this, okay? So, you know, when you vary z from 0, z, you know, it goes from, you know, it goes from 0 to infinity. What has happened is that, you know, the ground state, which was earlier here, this, okay, it goes to this, which was, where this was actually the infinite temperature state of z equal to 0. Okay, so what I'm, oh, sorry, this, yeah, this was. So this is, yeah, ground state of just that, you know, ZZ, let's call it ZZ Hamiltonian. And this was the ground state of sigma x, this one. Okay, so when you take z from 0 to infinity, what will happen is that this becomes the ground state. Okay, so in other words, this is somewhat like what I was saying. It's actually, you know, I don't want to say that some state come down here, okay, but because, you know, this state in terms of this is a linear combination of all the states. Okay, so, but roughly, what I'm saying is some very far off state, it goes down and it becomes the ground state. Okay? You know, that's the usual story about the, you know, phase transition that you learn in transverse Cauchy model. Okay. And of course, you know, it's well known now that, you know, the transition happened, and actually the transition is a critical point. It happens at z equal to, gc is equal to z, mod z, gc is such that mod z is equal to z. Okay. So, you know, this is something, so I want to give an estimate of this now, using some, you know, simple mathematics theorem. Okay. First note that, let's say this is the perturbation, okay? In this eigenbasis, you know, the expectation value of this operator is all 0. Okay. So what I'm saying is, I have called this, you know, HZZ, okay? So this is my HZZ and this is my HX, okay? Or actually, let me call only this part HX, okay? And let's call it ZHX, okay? Because I want to keep this Z separately, okay? So what I mean to say is, this, let's say we diagonalize this HZZ, okay? It's very easy, right? You know, it's all up, and all, okay? HZZ, we diagonalize it, and it becomes, you know, some number, and the rest is of course 0, because it's a diagonal matrix. And what I mean to say is that in the eigenbasis of this guy, the other perturbing term is actually a hollow matrix. 0, 0, 0, 0, 0, 0, all 0. The diagonal, of course, these are not non-zero. Sigma z, okay, these are some number, right? And so, and actually you can see that, you know, if you diagonalize this, okay, then actually this is, it becomes, a, you know, this other Hamiltonian becomes a hollow matrix, okay. But anyway, that's not important for me now. What's important is that in the eigenbasis of this Hamiltonian, this perturbing operator is a hollow matrix, okay, meaning that its diagonal is all 0. So first of all, because of this perturbation, if you know, you call this H total, did I call it H total? Okay, let's call it H total. Because of this perturbation, first of all, you know, by the trace sum of, you know, eigenvalue trace equal to trace, you know, formula, what is happening is actually, because of this perturbation, what is happening is only the, you know, the eigenbasis shift. Okay. Half time. Okay. Yeah. Sure. Thanks. So only the eigenvalue will shift, right? Their sum will of course remain constant. Okay. And what I'm going to use is a nice theorem, which is called Horn theorem. Okay. I was looking up, you know, some mathematics literature to try to constrain this Hamiltonian as much as possible, and there are many. Okay, you know, mathematicians are actually, there are various theory, like, you know, perturbation theory of, you know, Salvation operators, and then the most famous is Rayleigh Kato theory, something, okay. It's very simple, okay. And many people have done many other ways, okay. But what I found is that this theorem is actually very useful, okay. This theorem actually states that if I have a Hermitian matrix with some diagonal element D, let's call it D0, D1, dot, 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 okay, up to, let's say this is, I have used N, or, let me not put, it's some, actually I'll be using only the D0, right, because, I don't want to, for our case, we don't want the, ground state to shift, right, exchange. So D0 and any entries here, of course, it has to be Hermitian, okay? Hermitian for any matrix M, which is Hermitian, and it has diagonal entries like this, D0, D1. So M dagger is equal to M. And this, one of the results, okay? And actually, the mathematicians, they usually talk about in terms of the biggest eigenvalue, okay? Because they are interested in measurization and all that. But for physicists, we want the smallest eigenvalue, right? So, I'll just write down the, case for smallest eigenvalue. So what happens is that if you diagonalize this, and let's call it, the eigenvalues are lambda 1, lambda 2, etc., then the result of this theorem is that lambda naught is actually less than or equal to D naught. Okay. So in this way, what I'm saying, what this is saying is that because of this introduction of this interaction, the ground state of this Hamiltonian, okay, actually only shift downwards. All right. So this general picture of this cartoon is a cartoon, but this, what I'm saying is this cartoon is wrong. Okay. So what's happening is, let's say this was my psi naught of the z only, then it can only go downward. Okay, it cannot cross this line. Okay. Let's say this is the eigenvalue of the ground state energy of this, only this one. Okay. Then because of introduction of this interaction, the ground state can only shift downward. Of course, it can vibrate. It's just a lower. It's just upper bound. You can do this, Okay. The result, but the theorem says that it cannot cross up. Okay. So the earlier picture, which was, it's not a nice picture for, especially for this one, or for in general for this case. Okay. Yeah, and there are other inequalities, okay, which says that lambda 1 and this is equal to D0 plus D1 and so on, up till, the sum of lambdas is equal to sum of the diagonal, which is just a trace formula. Okay. Now, so far this is mathematics, okay. The next thing that I want to invoke is, what I was telling here, okay, that level crossing here, I don't care, but level crossing from some very high temperature state, okay, coming down and crossing this line, that's my problem. Yes, yes. Yes. Yeah, yeah. Yes, yes. So it's just a theorem. So actually, I don't know. Yeah, it doesn't depend on Z. If this perturbation has zero expectation value in the energy eigenbasis of this, then it satisfies this. Yes, yes, yes. Yeah. If you want perturbation theory, you do that. Yes, yes.
Some precise version of that kind of.
Yes. Okay, thank you. Yeah. I mean, this will become like lambda naught, will become d0 plus lambda square, but the sum is over E0 minus. So because of this En, so this quantity is anyway negative. So this negative come here. Yeah. So that's this story, but it's perturbation theory. Okay, something might happen. Okay, but this theory, this theorem is precise. Yes. Yes, yeah, there is no bound. It can happen even for unbounded, what mathematicians call unbounded matrices. Basically means the magnitude of the eigenvalues can be anything. All right, so because of this, my state, let's say I start from here, the unperturbed one. Okay, the ground state can only fluctuate here, here, here. All right, and as I was saying, I don't, for example, in this case, the eigenvalue of this, when it was shifting to this, okay, this was actually the, in the eigenvalue, eigenvectors of this was actually the infinite temperature state, okay, because, Z is equal to, X is equal to, Z plus, Z minus with 1 by square root of 2, 1 by square root of 2. Okay. Infinite temperature. Yeah, I'm talking in the effective sense, yeah. It basically means the probabilities are all, the probability of all these are, same. Let's go, yeah, this is the 2 to the power n. So it will be sum of this divided by 1 by 2 to the power n. Yeah, it's not a pure state, but if you compare energy, for example, you'll find that its effective temperature is, yeah, I'll come to this. In chaotic theory, in isolated chaotic theory, it's always in a pure state. Then how do you define temperature? You define it in the effective sense. Okay. Yeah, you can say microcanonical, fine. Yeah. Okay. So as I was saying, I don't want some, infinite temperature state to come down and cross with this fellow, okay, like this here, okay. And, but, a very rough hand wavy, this is where some approximation comes in, is that, so for example, yeah, let's do now a perturbation of this by this operator, okay. That's what actually we are doing here, right, after the phase transition, okay. So if I do a perturbation of this Hamiltonian, okay, with this, okay. By the way, in our case, actually, this is a hollow matrix in terms of this. So actually, it happens, let's say, yeah, let me draw a diagram and, okay, let me draw it maybe here. Okay, I want to, and one more cute result, okay, but yeah, I hope I have time. So let's say the spectrum of this two is like this. Okay. And the spectrum of the, this is for HZZ. The spectrum of H sigma, HX is, let's say, something like this. All right. Now, as I was saying, this state is actually not this state, okay? Because, this state actually corresponds to the infinite temperature of this Hamiltonian. Hilbert space. Yeah, okay, of this Hamiltonian, sorry. Yeah, Hilbert space, of course, are the same, okay. This state is the infinite temperature of this Hamiltonian, all right? So,
that's when G is much bigger than G.
No. This I'm just diagonally itself.
Okay, but X has a parameter G. Right?
Yes. Yeah.
And XZZ is a parameter J.
Yeah.
So when we draw that spectrum, the way you're drawing, with one being lower than the other, you're assuming something about J versus.
Yes. That's where actually I'm coming. Yeah, that's where I'm going. So, but please note that, this was the infinite temperature state of this Hamiltonian, okay? So, actually, for this case, as I was saying, let's draw the, let's say that I'm drawing this in energy, and of course, these are separate. So, because of the introduction of this, okay, this ground state can also go only downward, okay? Because this is a hollow matrix in the eigenbasis of this, just like it was there. And the same way, as I was saying, drawing here, the eigen, this can also go only downward. Downward, or at least, yeah, it can go above this, okay? So in general, this state and this state are very far away from each other, okay? So a very rough estimate of, that actually this can go below this in the energy, in the absolute scale of energy is roughly when, by the way, this was what I was calling, including the J, okay? But this I call only this one, okay? It's when the E naught, let me write it this way, E naught of HZZ is of the order of Z, some special GC, HX. Okay, sorry, E naught. All right. So basically meaning I am tuning my G so that this got enlarged. Okay. And it's roughly here, and then then they can start exchanging they can start competing who is the lowest one. All right. And so this is this is for me, this is my criteria for the validity of a phase perturbative expansion. Okay, so up to this GC, so G belonging to 0 to GC, perturbation theory will, I'm roughly saying that. Okay, when I derive this, I have used some hand wavy physics argument, but in this interval for G, the perturbation expansion will follow through. Okay. And by the way, as I was saying, that this this perturbation, okay, is a hollow matrix of this. It actually also appears in our black hole case, okay, because in the Hamiltonian of this this just combined Hamiltonian, okay, sorry, in the the energy eigenstates of this, just this combined Hamiltonian, the expectation value of this will, they will just factorize, right? And in a black hole, we don't want here, right? So this has to be 0. Okay. So the expectation value of this operator in the energy eigenvalue, energy eigenvectors of this Hamiltonian, it has to be 0. So it's actually the case like this one, okay, or like this one. Okay. It's a hollow, the perturbation is a hollow matrix, or in this case, the interaction. All right. So in the black hole case, we expect that this perturbation, the black hole evaporation is a prethermalization phenomenon. It will hold true until the expectation value of this start competing in the state, in the full state for this, it start competing with the energy of this Hamiltonian. Okay. So this is something that sorry, the results are like it's not very definite. Okay, I'm just building this for the last 1-2 months. Okay, but let me in the next 5 minutes let me just mention a cute result. Okay, which is again related with black hole evaporation. Okay, so as in the last week, Xiaolan Qi, he was talking about he alluded to eternal wormhole, etc. And Maldacena, him and Maldacena and Millikan, they have written this evaporation of a papers on this evaporation of not evaporation, okay, formation of SYK wormhole. Okay. So in their case, the paper is 1804-00941. This is Maldacena. And the other one where they do here they just analyze equilibrium states, okay, basically thermodynamics, and I think real time also, so like X10. And in here they do real time as well as non-equilibrium dynamics. Okay. So the setup that they consider is you have a SYK with the left, SYK left, and it's SYK right. And okay, let me use complex fermions. Okay. So and the interaction is given by left, psi right minus psi right, psi left. Okay. Yeah, and in this case, okay, what happens is that for those who, I mean, for many people it must be very familiar. Okay, is that if you consider thermal state, and if you decrease the temperature, depending upon this value of mu, okay, there is a two black hole to wormhole transition, okay, with decreasing temperature, with increasing beta. All right, and one can think of this as a Hawking phase transition, where this wormhole is this thermal radius gas, okay. And that's the approximate perspective that's been taken by the paper. Sorry, I don't have that paper. Okay, Gautam and Anurag and Spenta, where they consider Sorosian coupled to a free scalar. And the nice thing about this is that actually SYK can have another transition when you turn on a mass term, okay. But that is in the large mass limit, okay, it's just a free fermions, okay. So that there you don't have the gravity sector, but in this case you still have the gravity sector intact. Okay. And as you can see, in this Hamiltonian is basically like that one, where actually this perturbing operator is a hollow matrix. Okay. Okay, so I have. Yeah, because any yeah. Well, first of all, this will factorize. So let's consider this one. It will simply become. Yeah. So. Yeah, that's what I was telling over there also, because it's just factorized, and I don't want here in a black hole background. And this was studied in this paper. And next one, what this Maldass and Millikan did was actually they couple. So let me erase this portion and reuse this line. They couple this SYK Hamiltonian to BOT, another SYK BOT. Okay. SYK BOT 1, and this also to another SYK BOT 2. Okay. And of course, okay, these two are interacting by this mu term. And what they found is that, and if there is as I was saying, there is a phase transition which depends on the beta and mu. Okay, there is a competition between these two. Okay, and if the SYK BOT, if you take them to be the same temperature, okay, some beta BOT, this also same beta BOT, then, and if this beta is less than the greater, okay, meaning lower temperature than the black hole temperature, okay, then what you find is that this two SYK become like a thermal radius, okay, and that's what they call the traversable wormhole, and transition amplitude between these two, it actually becomes very large, okay. And the transition amplitude actually you can easily calculate from the expectation value of any of this psi left dagger and psi right dagger. Of course, these are a large number and you have to sum over and all that. Okay. So in the wormhole phase, what they find is that I think this was in this other subsequent paper it was found that after the transition this become large. Okay, compared to this is greater than this value. in the black hole phase, 2 black hole phase. Okay, very much bigger actually. Okay. This is some 3 or something 4, and this is actually 0.1 or something. Okay, it depends upon the parameters that you're choosing. Okay, but for the same parameter, it becomes very large, right? Now, in the setup that I consider is, let me tell you about the setup that I'm considering. Okay. But as I was saying, it become like a, in the 2 wormhole phase, you can think of it as also a, this. You can think of it as also, ADS thermal gas. Okay. Yeah. Exponentially smaller. Sorry, I haven't seen the comparison. Okay, but they are okay for given mu. Given you mu and z, and you fix it, and you find that it's good. Yeah. And yeah, so the setup that I'm considering is I have a SYK system. I just want to consider, evaporation. Okay. So as I consider SYK system, okay, let me call it SYKS, and I couple it with, by the way, in here, the coupling was SYK, but something like this, okay? Psi of left daggers, psi of bot 1 dagger, psi of bot 1, psi of bot 1, and then psi of this left, okay? Something like this. And of course, the other combinations. Okay. In my case, what I want to do is I want to turn on that mu, and I also want to turn on that bath coupling. Okay, bath coupling. Okay, so let me call it. Yeah, I think they call. Let me call it eta. Okay, I turn on eta also to another SYK, and let me call this intermediate SYKI. And then I couple this with this eta, very large eta, another eta. Okay, eta large, to another SYK, which is I assume to be very large, okay, and the temperature of this is fixed. Okay. And as you can expect, if this beta, and then let's say you prepare this in some beta 1, which is much smaller than this beta, meaning this has higher temperature, and then you start this coupling at some instance time t equal to 0. Then what will happen is, this, the energy will be transferred to here, and then this will go to this 2 wormhole phase. Okay, and so after a long time evolution, depending upon the run, controlled by this eta, perturbation theory of eta, long time evolution. Okay, what happens is this two goes to the ADS. This goes to the ADS. 2 wormhole phase. Okay. Or in other words, this has evaporated. Okay. ADS thermal, and this also will go to ADS thermal. And of course, this will remain same. Here, I'm not coupling with mu. Okay, so it will remain a strongly chaotic SYK. Yes, yeah, I have taken that. Yes, that's what I'm saying. This beta 1 I have taken to be much smaller than this beta. Okay. I'm not sure that there is this transition happening. Okay. No. Actually, the transition is not. There is overlapping between these phases. Okay, so there is a certain intricacies. Okay, I don't want to get into that. Okay, that's why everything is very diagrammatic. Okay. What I want to come to is, as I was saying, this in the wormhole phase, the tunneling or this amplitude is very large. Okay. So does this means that these two SYK are highly entangled, right? But you don't expect it, right? From the pH curve, you expect that by the way, it's after they have evaporated. So let me see in this context, in my context here. Okay. transition amplitude, one electron jumping from here to here, this quantity is very large. Okay. So does it mean that this is highly entangled? Okay. But you don't expect it, right? In a black hole evaporation, you expect phase curve, not the not this, the tunneling grow and remain very large. No, but it depends upon this beta, right? Yes, yeah, of course. Yeah. So it will go something like this, and it will, something like this. Yeah, but at least if you think that this amplitude measures entanglement, then what's happening is it's going something like this. Yeah, like a lot of phase. Not yet. Hold on. Okay, so anyway, so what I want to calculate is actually the real correlation. Okay, it's a 4 fermion operator. Basically, I want to calculate. That's the reason why I take SYK, not directly connect it with this. Okay, I want to calculate the density correlation. Let's call it. I was calling it S. Okay, density correlation of this, and this one is intermediate psi I. Okay, in this. Okay, they actually now this I do in a. I want to do in a I can do it. Okay, in a non-equilibrium setting. Or I can do it in a equilibrium setting by just changing and preparing the state in this, and all that. Okay. So, but this is a 4 fermion observable. Okay. And in all this, okay, people use is the Z sigma. What people call the what we use also is the Z sigma formalism, where you have sigma in terms of Z. Okay. So Z is something, in real time there are many ordering, okay. Roughly you have psi and psi only, okay. So what people do is, you're using this Beam equation and all, okay. You just look for time dependence of these quantities, okay. So how do I get this quantity? It's a 4 fermion quantity, okay. It's basically asking, so let's say I take this T1 and T2 to be the same. Okay. So this will be the occupation number in let's say the left. That will be the occupation number, only the left. But I want correlation. Okay. So when I'm dealing with only Z, if I ask this quantity, it's like asking, I give you a min, you calculate the variance. Okay. Nobody can do it, right? Unless you have the distribution. Right. But in our case, since we have a control over this system, there is a neat trick, okay, which is nothing but the linear response theory. Okay. Linear response theory, as we know, if I have a system and if I disturb the system with the O disturbance, then I measure a O observable, okay, OO, okay. Then the change in the OO, it is related with retarded Green's function of retarded of OO OD, right? Retarded, okay. But this is again retarded, okay. If you take time, there is some formula, okay. At least in thermal ensemble, using the retarded, you take the imaginary part and so on and so forth, okay. So what I'm saying is, I know this quantity, okay. And so in this combined system, by changing the psi L, okay, by giving it the delta function kick, okay, I look for the response here, right? And that response actually captures this quantity, okay? You do for some Fourier transform here and there, and then you get it. Okay? And after doing that, and it's all done not in a non-equilibrium setting, okay? After doing that, what we find is that, okay, let me not draw it here. Let me just say in it word here. If in the black hole phase, actually you have to scale this also, this quantity, okay, divided by square root of the beta. I'm calculating in a given thermal setting, okay. What we find is that in the black hole phase, this is very small. Sorry, this is relatively large. Okay, sorry. And in this phase, this is very small, okay. All right, so what is happening is that even though the transition amplitude is, very large, okay, in the thermal phase, you don't have too many excitations, okay, so they don't participate in the, jumping around here and there, right? So that's why it has this has a very small correlation in the wormhole phase, all right? So I'm actually, if I, instead of doing the Z sigma formalism, if I go higher and calculate the, time, solve the, numerically solve the equation of, something like psi L, psi L1, T2, psi intermediate or the other one, okay, you call it whatever, T3. If I solve this equation, and if I solve for the equation of this, okay, then of course, I'll be able to see that this density correlation, they increase. Okay, as soon as I connect these two, the density correlation will increase, and then as they cool down and go to this very low excitation state, then it will go down. Okay, so I expect that. If I really calculate this time dependent, in a non-equilibrium scenario, we expect this, because we already expect, we saw it in equilibrium calculation here and here, right? Okay, so many people do Z sigma formalism, just solve time dependence of it, but using linear response theory, trying to calculate this, I think, not many people have tried. And it's so a very nice thing. And I have one comment, okay. You might think that, okay, I'm doing all this in a thermal state, okay. So, what is this correlation? Is it a classical correlation? Is it a thermal correlation? Or is it a quantum correlation, okay? But I would say that, you can call it a quantum correlation. And of course, whether quantum correlation equal to quantum entanglement, there's a big question. You have heard about quantum discord and all that, okay. But for me, let's just say, quantum correlation means quantum entanglement, okay. So what I'm calculating here is not, as you can see, this is divided by n, so it's just the, average correlation, right? So, even though PS curve may look like this, I don't expect it to be like this. It may look like somewhat like this, I don't know, okay. But I really have to calculate that, but at least, it's 0 here, okay, because there was no correlation, and it increased, and it decreased here, that much I am sure. Okay. And okay, now coming back to why you can call it a quantum correlation. Okay, the reason is very simple. Okay, it's because it's a system, is a chaotic system. So if you do it, if you use ETH, and if you do all of this thing, okay, in a typical state, typical pure state, okay, you'll see this whole thing, because these are leading order calculations, few body leading order calculations, okay. So by ETH, if you do this, all of this in a pure state, okay, it should also reproduce the same thing. Okay. So you can call this correlation quantum correlation, okay, and it actually, keep track of the quantum entanglement. So let me stop here.
So let's thank Nilakash. So any questions?
Yeah. Mm-hmm.
What's the point that this high correlation proves that there is prethermalization? What is the relationship between the final bit about when you calculate the density correlation?
Yeah. No, I'm calculating this just to reproduce PS curve like qualitatively PS curve like behavior. It's not related to prethermalization. Oh, the first part was to say that this black hole thermalization is a prethermalization process, and the second bit, this is the cute result that I was saying, is that I can calculate this even though you are still stuck with this Z sigma formalism. I can calculate this 4 fermion operator, and it captures this behavior. Oh, by the way, many people have, including Vijay, group from here, they calculate PS curve in some free fermion, and I know other people who have calculated in free fermion. But this is, as you can see, this has a gravity sector, and it's the real deal. It's not some free theory. That I don't know. For now, I'm doing just numeric, very preliminary result. I found that this is smaller than this. Okay. If I remember, it's only half. Okay, the difference was this was some 0.016, and this was half of it or something. Yeah. Maybe I can tune my beta and mu. Actually, I can go to very low temperature, so that that might if I go to very low temperature, I expect that it will go further.
Questions?
Yeah. Hi, Stefan. Yeah. Yeah. Uh-huh. Mm-hmm. Mm-hmm. Sorry, why in what? Oh, it's because as I was writing here, if I have a black hole, I don't want here, right? A black hole, if I have a so I have the black hole Hamiltonian, I have the I have the Bath Hamiltonian, and then I couple it with O black hole, and then O Bath. Okay, and if I calculate this quantity in the eigenvalue of this, they will just factorize, right? Because anyway, a separate state. So this will be O of in the black hole, O of Bath. Sorry, black hole in the black hole state, O Bath in the Bath state. Okay. And in the black hole, outside the black hole, I don't expect this to be 0 because it will fall in. It's some lump of metal, lump of stuff that's hanging around. It'll fall into the black hole. Of course, there are this. You can have it if there is phase, right? People do holographic superconductor and all, where you have some web of some phi and all that. But I'm thinking about the garden variety black hole, which attract everything in. Yeah, that's why. Yeah. So this is 0.
Okay, so if there are no further questions, let's call it a day. So tomorrow, and thanks, Nilakash, once again.
Thank you.